Hello and welcome to the MOOC on optical communications. In this module we will discuss pulse shape and bandwidth issues. Before we talk about pulse shape and bandwidth issues, let us pause a little bit to consider where the data for optical communications come from. You know, data might originate from various places. For example, what I am speaking is speech, and this speech, if it has to be transmitted, for example, you are viewing this video lecture on a video on a YouTube channel. So, before this you were able to view this channel, the speech that was coming out of my mouth, which represents the pressure waveform or the acoustic waveform, because of the varying pressures in my throat, the corresponding acoustic waveforms would come out, and this acoustic waveforms, the pattern of which would be the speech waveform. So, this entire lecture is one speech waveform, which is more or less a continuous function of time, and this waveform had to be first converted into an electrical form, because you are going to use an electrical waveform such as a current waveform or a voltage waveform that would capture whatever the speech that I am speaking, right. So, it would essentially also be a waveform that would typically be continuous in time, but its modulation, its changes would actually be the same as the speech waveform that I am presently, for example, trying to communicate to you. Okay. So, this electrical waveform will be the input to the optical modulator, right. The optical modulator does not accept, unfortunately, just a speech waveform. So, I can't just take an optical fiber, for example, if this is an optical fiber, I can't say take this and say my name is so and so, please transmit this message. The optical fiber refuses to acknowledge that. So, what the optical fiber recognizes is light, and we have to change light in such a way that the changes in the light waveform will in some way represent what the speech waveform is. So, this process of making the carrier and one of the parameters of the carrier to change in accordance with what the message signal is called the modulation process. It is kind of used as a matching thing, my voice is not matched to the optical fiber, but the light is matched to the optical fiber. So, I take light from a DFB laser, and then I will modulate the light waveform using the speech as the source, but speech being an acoustic waveform cannot directly modulate there. I can't use it directly to the optical modulators, or at least not the ones that we have covered in this course. So, what we have to do is to convert this speech waveform into electrical waveform. Consider a different type of communication. For example, you want to communicate to your friend a certain message on WhatsApp. Okay. So, this message that you want to communicate, if you were to type that message, the message as you type is actually a sequence of sentences or something, sequence of words which form sentences, and sentences presumably have some meaning to them. Okay. Where are these words coming from? Assuming that all of us are using only English as the communicating language, then these words are coming from the English language. And what is so characteristic of the English language, or in general any language? A language has a set of letters which form a alphabet. For example, English has 26 letters A, B, C all the way up to Z forming the alphabet. A different language, maybe the language that you speak at home, which may not be English, will have a different set of letters. Okay. However, the goal of each of these languages is to communicate information. And how do we do that? For example, in English we start maybe for example, we start with letter M. With the letter M, which is one of the letters that has been taken from the English alphabet, the next letter would have to follow this letter M. We form a word. So, group of letters form a word, a group of words form a sentence. That is how we construct, even in our languages which is not English, this is how we typically construct. Sometimes in our language we have the ability to take multiple letters and form a single letter out of that one, okay. Or we will use these individual letters as in when we are forming sentences using English. So, let us say I am told, or you are told, that the first word is a 2-letter word, the second word is a 4-letter word. Okay. So, once you have put down the first letter M, right, then the chances for the second letter to be one of the 26 letters is now distributed according to a probability. In fact, even the first letter is a probabilistic occurrence, I do not know what the first letter of the message that I am receiving. However, once I receive and I have some knowledge about the word length, or the length of the word, then if it is a 2-letter word and if I know what the letter M is, then there exists a certain probability for the letter A, for the letter B, for the letter C and all the way up to the letter Z. Some letters are more likely to occur, some letters are less likely to occur. For example, you might more or less rule out this M followed by a Z. It is kind of not very common occurrence, so I can rule out this. Similarly, I can rule out this M followed by B, usually it is not, does not really make sense. MA could be a legitimate sentence, so you might want to keep that one. You can try other letters, you can try for example Y forming MY, right. So, that has a certain probability for it. So, if you form all the 2-letter words that begin with M in the English language, you will see ME, MY, MA could also be another letter. You probably see MR as in a short form for Mr. You might also see a S as a short form for S. So, once you have fixed the letter, the next letter there is a certain probability for these letters to occur. Okay. We call this, so if this instead of occurring at the beginning, it had occurred at the ith position and the next one is the I plus 1 or the kth position, we can actually form a transition probability Pik. Okay. And then we can actually look at we can construct a matrix which tells you that if I start with A and the next letter to be A, for a 2-letter word I am constructing this one, of course for a 3-letter word I have to construct a different matrix, right. Similarly, for an n-letter word I have to construct a different matrix altogether. For a 2-letter word, these are the transitions that I am looking for. A to A, there is a transition which we can call as P11. A to B, there is a transition which we call as P12 and so on all the way up to Z, and Z happens to be the 26th letter. So, you have P1 comma 26. Right. Similarly, you start with B, you can construct a matrix which we would say P21, P22 all the way up to P226 and so on for all the letters up to Z. This is the transition probability matrix. What it simply means is that if you start with a 2-letter word, okay, such as the letter M, somewhere it would appear here, right. So, if you start with the letter M, then the probabilities for these words would be high, the probability of these transitions would be pretty high, whereas transition of M into Z might be very nearly 0, right. Probability of M into A might be some number, M into B might again be very nearly 0, M into Y might be pretty high probability, so maybe about say it occurs 0.4 times, whereas ME might occur 0.4 times. So, in a way you once you fix the letter M in a 2-letter word, the next letters will all be according to a certain probability, right. So, to properly capture this, and you can of course also observe that the sum of these probabilities should be equal to 1, because if you start with M and it is a 2-letter word, next letter has to be something from A to Z, right. So, this process in which, or this kind of a behavior in which the letter of occurrence depends on the previous letter if it is a 2-letter, or it might depend on previous 2 letters, it might depend on previous 3 letters, in general it might depend on previous n letters. We have to model this characteristic of the dependence of the previous letters to previous letter by modeling the source of this information as a memory source. Okay. Sometimes this is called as a Markov model, okay, wherein the Markov source represents the dependencies and these transition probabilities will all come into picture. But even if you were to not get into all the details of this source modeling, and this is really a subject on its own which is very important, what you have just realized is that if I take a word, so which would be say my name, this phrase which is there, right, this is nothing to do with optical, right. This my name exists whether it is optical, wireless, whether it is communication by anything else. If the transmitter and receiver are pretty close to each other, then my name can be conveyed over the channel by shouting across. So, I shout, the pressure variations on my throat will generate an acoustic waveform. These acoustic waveforms will travel to the listener's ear will then interpret, and that is how I will be able to communicate. The problem is that sender and receiver are not close by, they are connected by an optical fiber. Of course, they are connected by an optical network, but we will assume that they are connected by an optical fiber, not the elements which go through the network. So, how do we convert this? First of all, I can't take my name and then try to modulate the optical transmitter, I can't, right, because this is in English and modulator does not understand English. So, I have to convert this into a current or a voltage waveform. Okay. So, I have to convert this into a current or a voltage waveform. In order to do that one, I have to specify waveforms corresponding to each of these letters that are occurring. So, for example, if M might be specified by a waveform that looks like this, Y might be specified by a waveform that would look like this, okay, and N might be considered as a waveform, A might be considered as another waveform. So, I can do this is one arbitrary way of setting up the waveforms. I can also do this, A might be of 1 volt, I am now going to the voltage representation. This could for example be current, and this entire duration might be representing one letter. Okay. So, this entire duration represents one letter, and let us assume that these durations are all going to be the same. So, the durations of each letter in this representation is all going to be the same, and if you imagine there is a time axis running through this, then the first letter M was typed, then letter Y was typed, there is a space, then N, A, M and E. If you call each unit as some T S unit, so you can have any kind of a waveform representation. The simplest requirement that the waveform has to satisfy is that the waveforms have to be unique. You can't have a single waveform representing 2 different letters, then it won't really match correctly. You can't reconvert the waveforms into symbols. So, you can do the symbol to waveform, but you can't do this waveform to symbol. Okay. You can't demap it, as we would call. So, you have to choose that, if you take that criteria, then you can choose this waveform to represent A, you can choose a 2 volt to represent B. Similarly, if you come up to the end, then you will be choosing a 26 volt to represent Z. Okay. This might be possible, the only thing is there are so many levels, and you have your electrical circuit will really be complicated while it is trying to generate these multiple levels. Okay. So, this is not something that is efficient. So, here is a second characteristic, you want to choose the representations which are efficient and easy to generate. The universally accepted technique to transmit information using digital optical communications is to convert every known form of the data into binary format. Okay. The type written sheet or the email that I would write or the message that I am going to type on a WhatsApp application, they are all in English, assuming that this is the language that we are working with, they are all in English, they are all sequence of letters that are coming out, but these symbols, so these are English letters, these letters will have to be converted into binary format. So, we can call this as binary symbols. Okay. The primary binary symbols are symbol 0 and symbol 1. So, I am putting this inverted comma or quotes to indicate that these are symbols, these are not numbers. This is not a 0 number, this is not a 1 number, this is actually 0 symbol, a 1 symbol. They are as abstract as the English letters. Okay. If you technically want to write this one, the word my should be written as the symbol m and the symbol y. In much of the same way we have written 0 and 1. Now, what the source coding does for us is that when this conversion from English letters to binary symbols happen, each letter in the English alphabet or each letter in the English alphabet will be represented by a group of binary symbols. Okay. Maybe you can call this as a symbol, a group of symbol or a word or something like that. Okay. So, the binary representation for this A might for example include symbol 0, symbol 1 in sequence. Okay. For B it might be 1 0 0. Okay. Please note that these are not efficient, these are not the way in which actually you would be doing the source coding. I am just giving you an example of how you might do it. Okay. These are not very efficient at all. This process of going is called source coding, and this is something that is a very important subject in communication theory altogether. We are just giving you the idea of what goes on here. So, you start with English letters and then you get to binary symbols. Now, MY might have a binary symbol representation of this one. Okay. It need not be this, but just taking an example. If you want to be little more technical, you can try a ASCII code or something. These are efficient representations, or they are good representation, not a very efficient representation out there. So, this MY which was in English has now been converted into a group of binary symbols. Okay. It turns out that these binary symbols can also be made into binary digits. Okay. A 0 symbol can be a 0 binary digit, a 1 symbol can be a 1 binary digit. Okay. This binary digit is in short called bit. Okay. So, eventually what you have done is to take the data and then convert that data into bits or sequence of bits. Okay. Sequence of bits form a symbol, right. There is one aspect which we left out. We said that speech waveform is a waveform, but that would be converted into a current or a voltage waveform, right. So, if this was a speech waveform, that has to be converted into a current or a voltage waveform. If this is not a speech waveform, but this is just something that you have written here, or it could be an image, then that has to be first converted into a current or the voltage waveform, right. So, there are certain devices which perform this conversion of non-electrical data, that is non-electrical format to electrical format. Okay. For example, the speech signals or the speech waveforms will be converted into current or voltage by appropriate transducers. Okay. So, you find an appropriate transducer to convert a speech or a current speech into current or voltage waveform. Okay. However, if you are looking at a message on the text, then that would be internally converted into a group of symbols. Okay. That is also non-electrical, but there is again the type thing that you are going to press, the switch will activate a certain waveform which will then be a representation of what you have typed. Okay. So, there are without going into details, that also is non-electrical, but that is converted into electrical form. Okay. One difference is that a speech signal is inherently continuous time signal, okay, which means that it has a value for every time variable. Okay. So, it is kind of continuous in time, and the corresponding conversion is also continuous in time, but you want to capture a discrete time version of this. Okay. So, you convert these continuous time signals into discrete time signals by a process known as sampling, which is usually implemented by an analog to digital converter. So, an analog to digital converter samples the continuous time waveforms and generates a discrete time waveform. Okay. An example would be, let us say this is the speech signal or this is some other signal which is varying continuously with time. What the analog to digital converter does is, it looks at this sample value, right, records it, looks at this sample value, records it, it samples here, records the value, samples here and records the value, and so on. However, these are actually numbers, they can be any number. So, this for example could be 2.3103 in the decimal format, this could be the number. However, what we do is we consider certain ranges, okay, we consider a certain range, and then so we divide this one and then consider certain ranges, and if the sample value falls anywhere within that, we associate a binary word to it. Okay. So, we associate a binary word to it. The length of the binary word, which determines the so called quantization levels, okay, is dependent on the ADC. You can have a 16-bit word, you can have a 32-bit word, you can have a 64-bit word. Okay. With the increasing number of bits, you are better able to represent these decimal numbers. Okay. So, you actually have a speech waveform converted into decimal numbers, and these decimal numbers are converted in turn into bits or sequence of bits or binary words. Okay. We unfortunately use the same symbols for bits, which is 0 and 1, as the same symbols for symbols 0 and 1 as well. So, this is a symbol here, okay, whereas this is a bit, this is a binary digit, this is numeric, while this one is more or less abstract, a symbol. Of course, we would have been better to take this 0 and 1 as say 0z and 1z, then this would have been, sorry, 1s and 0s, maybe to just indicate that these are symbols, but eventually symbols have one to one representation with the bits. So, we simply call both of them as bits itself. Okay. So, that is the goal of the source coding problem. So, any non-electrical data will be eventually converted into sequence of bits. Has our problem been solved yet? Unfortunately, our problem has not yet been solved. Why is that our problem has not been solved yet? Well, go back to the optical transmitter. You have a laser here, okay, which is producing nicely a continuous wave signal of frequency omega s having a certain amplitude square root of Ps. So, this is a nice carrier with a very high frequency up there, but then you have to modulate this carrier, right. You have to modulate the carrier according to some data, and this data in this time is actually a sequence of bits. So, let us say the sequence of bits is 1 0 1 1 0 1. How do I take this sequence of bits which are still, even though they might be numbers, but I can't just use numbers and then modulate an optical transmitter, right. For that I have to do an interesting thing. I have to represent this one by a waveform, okay, and represent this 0 by a waveform. Okay. So, I have to represent the bits into waveform, and this process is the bit to waveform conversion, and here is where we are going to look at the pulse shapes, because the way you convert bits into waveforms has a tremendous effect on the bandwidth of the system. What would be the bandwidth of the system? Okay. So, you choose your waveforms efficiently such that you are well within the bandwidth that is mandated by the regulation. So, if the regulations say that you cannot use more than 50 gigahertz bandwidth, all your optical energy must be within that 50 gigahertz bandwidth. Okay. If you are outside, then you are not just interfering with the next band, you might also have a commercial penalty, you might also have a penalty for going over your band. So, if you have been allotted at 50 gigahertz band, you better choose pulse shape such that the optical energy, at least say 99% of the optical energy, 90% of the optical energy as regulated by the regulator commissions, you have to have all that energy within that. Okay. Of course, unfortunately there is no universal definition of a bandwidth. I just said 99% could be a cutoff, 90% could be a cutoff. Some other commissioner might come and say, no, I do not like 99, I do not like 90, let me make 98, and there is nothing you can argue about it, because bandwidth is not uniform. Although if you take it say 10%, then you will be in trouble, okay, because the energy is considerably spilling over and you are either wasting it or causing it to crosstalk with other bands. Okay. So, there are some trade-offs that are involved. Although bandwidth is not defined, you do know that what happens if the energy goes or occupies a certain range of frequencies. Okay. So, with that, let us look at pulse shapes. As I said, the bits have to be converted into waveform, and there are various choices. Okay. So, let us look at some common choices. These choices are called as line codes. Okay. If the goal is to just be there in the electrical format, these are called as line codes. So, you take the bits and then convert them into electrical waveforms, a voltage or a current waveform. One popular coding technique is what is called as the polar coding technique. In the polar coding technique, you assume that the bit B, if the bit B is equal to 1, then you represent it with a rectangular pulse of amplitude of duration Tb and an amplitude of +1. If it is current, it would be 1 ampere or normalized to 1 ampere or normalized value there. If it is voltage, it would be some voltage, but it would be a positive pulse, okay, of duration Tb and more or less rectangular. For our analysis, we will assume rectangular. If the bit B is equal to 0, then you represent that one by a pulse of the same duration Tb, but its amplitude is -1. At the same time, let me remove all this one here. So, the tails are not there, the zeros are not the part of definition. Okay. So, this is what it is. So, this is the polar format. You have let us say the sequence which we looked earlier. So, the sequence was 101101. So, I have the sequence. First let me take the time axis and section it. Okay. Now, the sequence has to be 1 0 1 and 1. I do not have space to write the other one. So, I am going to leave it at these 4 symbols. Let us also draw a line showing that this is the time axis. Okay. And now, these symbols have to be written. What is the symbol for 1? It is a +1, which would be occupied by the entire duration. A 0 is something that would be occupied as an entire duration, but it would be amplitude -1. So, here the amplitude is +1, here the amplitude is -1. The duration here is Tb, the duration here is Tb. The subscript b indicates that this is a bit time or a bit duration. So, every Tb seconds you are going to output one waveform. This waveform would represent either a bit 1 or a bit 0, but it would output one bit waveform. Okay. Then going back to 1, you have a +1 here, and then going back to 1 you have a +1. So, the amplitudes are +1. So, this is the waveform representation for your polar format. Okay. Now, let us look at one more popular format. This is called as unipolar format. You do of course realize that there is nothing optical about this one, at least until we specify that it cannot be optical. These are just regular line codes. Okay. How you represent bit with a waveform. However, for optics there is nothing like a minus power. If for example, you want to represent optical power, right, as in the intensity modulation systems, I can't have a minus 10 watt optical power, because optical power is always a positive quantity. Okay. So, I can't really use this polar format which will give me plus 10 watt and minus 10 watt. So, I have to find other means. However, with an electrical signal it is possible, the current could be plus 10 amps or current could be minus 10 amps. Okay. Now, with unipolar you overcome this problem. Unipolar actually, as its word meaning suggests, a single polar quantity. So, here a bit b is equal to 1 will be represented by a positive quantity, bit b is equal to 0 is represented by transmitting nothing. Okay. So, if you go back to the same sequence 1011, this would be your transmitted sequence. Okay. Each occupying a duration Tb, it does not really look like that, and then you have 2 Tb over here, because you have taken 2 bits of time to transmit this one. Okay. So, this is polar, this is unipolar. In addition to this, you also have 2 formats which are even used at the optical level. These are called as RZ and NRZ. In the NRZ, the pulse occupies the entire unit Tb. Okay. For example, if I am doing NRZ unipolar, then the pulse occupies entire Tb. Okay. If I am doing NRZ polar, then this would be slightly different. So, I'll have for a plus signal I have positive 1, for a bit b equal to 1 I have Tb here, for bit b equal to 0 I will have for the entire duration with an amplitude of -1. Okay. This has an amplitude of +1, this is +1, but it would continue to be there for the entire duration Tb. However, if I am looking at RZ unipolar, RZ stands for return to 0, NRZ stands for non-return to 0. Okay. I might actually have a duty cycle which is only 50%. So, this would be for bit 1 and 0 for bit 0, but note that this duration is only Tb by 2, it is only occupying half the bit duration. For RZ polar, I have a return to 0 pulse here for plus bit 1, so this is for bit 1, and then I have a -1 pulse that would look like this. Okay. So, you will have these different ways in which you can represent, but which one would you want to choose? What would you want to choose is determined by what is called as power spectral density, something that we are going to look at in the next module. Okay. So, we will stop here and continue the discussion of power spectral density of these various formats in the next module. Thank you very much.